Welcome to our deep dive into the fascinating world of operating systems. You asked for a look under the hood, and we're happy to oblige. We're using two key sources for this deep dive. Excerpts from an operating systems development textbook to provide a foundational understanding and actual IV6 source code snippets. To show how these concepts are implemented in a simplified, Unix-like OS, get ready to see what happens from the moment you hit the power button to the intricate dance between software and hardware.
It's going to be a fascinating journey. We often take for granted the complexity that makes our digital lives possible, and this deep dive will shed light on some of those hidden marvels.
It's like magic, right? You press that power button and your computer springs to life. But there's a whole symphony of actions happening in those first few moments.
It's like a computer waking up from total amnesia.
Yeah.
The computer starts with a blank slate and needs a guide, a set of instructions to get going. That's where the BIOS, the basic input-output system, comes in.
Okay.
Think of it like a tiny mini OS that lives on a chip on your motherboard.
So the BIOS is like the conductor getting the orchestra ready to play before the main performance starts.
Exactly. It checks the hardware, makes sure everything is in order, and then locates and loads the operating system from your hard drive or SSD.
So it finds the right files and tells the computer, okay, here's what you need to really wake up.
Precisely. It looks for a very specific piece of code on the boot device called the boot sector, a tiny program responsible for loading the rest of the operating system into memory.
It's mind-blowing that such a small chunk of code has such a huge responsibility. And our textbook even had a Hello World example using boot sector programming. It actually showed how you could display a message on the screen before the OS even loads.
It's a great illustration of how we can directly control the computer at a very low level using assembly language, manipulating registers and accessing memory locations.
You're speaking my language. I love the idea of getting down to the bare metal and understanding how things work at that fundamental level.
It's definitely fascinating. And there's a safer way to experiment with this low-level code without risking your actual system. CPU emulators like Box or QEMU, you can simulate a specific CPU and step through the execution of your code line by line.
It's like having a virtual playground for experimenting with the building blocks of a computer. Now, before we load the main operating system, there's this concept of 16-bit real mode that we need to talk about. What's the story there?
Real mode is a legacy mode, a throwback to the earlier days of computing when processors were simpler and memory was limited. The key thing to remember is that in real mode, a CPU can only directly address 1 megabyte of memory.
That's tiny by today's standards.
That's tiny by today's standards, and that's why modern systems transition to protected mode, which we'll get to in a bit. But understanding real mode is important because it's the starting point for the boot process. The BIOS initializes the CPU in real mode, and the initial stages of loading the OS happen within that limited memory space.
So real mode is like the launching pad for the more sophisticated protected mode.
Exactly. Now, in real mode, memory is organized using segments and offsets. It's a bit technical, but the main takeaway is that this method had limitations. In terms of how much memory it could address, each segment could only hold up to 64 kilobytes of data.
I can see how that would be a problem if you're trying to load a modern operating system with all its bells and whistles.
Precisely. But even with those limitations, understanding how memory addresses work in real mode lays the groundwork for understanding how things work in protected mode.
Okay, so we've got this launching pad of real mode. But to unleash the full power of modern CPUs, we need to move to 32-bit protected mode. It sounds like a major upgrade.
It is. Protected mode unlocks the capabilities of modern processors, giving the operating system access to vast amounts of memory. And importantly, it introduces the concept of memory protection, which is crucial for security and stability. Imagine if any program could access and modify any part of memory, including critical system areas. It would be chaos.
So protected mode is not just about accessing more memory. It's also about setting boundaries to make sure things run smoothly and securely. I'm starting to see why it's so important.
You're getting it. The transition to protected mode involves setting up a structure called the Global Descriptor Table, or GDT.
Okay.
It's essentially a directory of memory segments that the CPU uses to manage and protect memory.
So the GDT is like a map that tells the CPU where everything is and what permissions different programs have to access specific areas of memory.
That's a great way to put it. And switching to protected mode involves a carefully choreographed sequence of steps, including setting up the GDT and flipping a bit in a special control register called CR0.
It sounds like flipping a switch. but I bet there's a lot more going on under the hood.
You bet. Modern CPUs use pipelining where different stages of instruction execution happen in parallel. This can create issues when switching modes because instructions might get executed in the wrong mode, so we need to make sure the pipeline is cleared before making the switch.
It's fascinating how something seemingly simple can involve so much complexity at the hardware level. And we're doing all of this just to get the operating system loaded into memory.
It's a testament to the ingenuity of computer engineers who design these intricate systems.
Okay, so we've booted up, transitioned to protected mode, and we're ready to start loading the actual operating system kernel. But kernels can be huge and complex. What's the tool of choice for writing these behemoths?
While it's possible to write an entire kernel in assembly language for large and complex systems, it's not the most practical approach. C is often the preferred language.
Why is that? I've always thought assembly language was the closest you could get to directly controlling the hardware.
It is. But that level of control comes at the cost of readability and maintainability. Assembly code can be very dense and difficult to understand, especially for large projects. C offers a higher level of abstraction, which makes the code more readable and easier to manage.
So C is like a more human-friendly way to write code that still allows us to do powerful things with the hardware.
Exactly. And remember, C is still a compiled language, meaning it gets translated into machine code that the CPU can execute. The compiler takes care of that translation process.
That's pretty incredible. It makes me wonder, how much of what we've discussed so far do programmers actually need to worry about when they're writing code for an operating system?
That's a great question. And it's something we'll explore further as we dive into the world of IV6. But for now, let's move on to the crucial role of device drivers.
Sounds good. Device drivers are what allow the operating system to talk to all the different hardware components, right?
Exactly. They're the intermediaries between the OS and the hardware. Imagine you have a symphony orchestra, but each musician speaks a different language. You need translators to make sure everyone understands the conductor. That's what device drivers do.
I love that analogy. So the OS doesn't need to know the low-level details of each device. It just talks to the driver, which acts as a specialized translator.
Precisely. This makes the OS much more flexible and adaptable because it doesn't need to be rewritten every time a new piece of hardware comes along.
Okay, so drivers act as translators. But how does this communication actually happen? How does the OS tell a device driver what to do? And how does the driver interact with the hardware itself?
Hardware devices typically have controllers that expose registers. Think of these registers as control knobs that the CPU can tweak to control the behavior of the device.
So the CPU is sending commands to the device by manipulating these control knobs.
Exactly. And the driver knows which knobs to turn and how to turn them to get the desired result. It's like having a detailed instruction manual for each device.
I'm starting to see the big picture here, but I'm sure there's a lot more to it.
There is. But we've covered a lot of ground in this first part of our deep dive. We've explored the boot process, the transition from real mode to protected mode, and the roles of assembly language, C programming, and device drivers in building an operating system.
It's been an amazing journey so far, and now I'm really curious to see how these concepts come together in a real operating system like by V6.
Let's dive into that in part 2 of our deep dive.
Welcome back to our operating system adventure. We've built up a solid base, but now it's time to get hands-on. XV6. It's like a miniature Unix world, ready for us to explore.
It is a bit like having a model train set where you can see all the intricate mechanisms at work. We can examine the source code to understand how those concepts we discussed are implemented in practice.
So we're going from the textbook to the workshop, seeing theory become code. Where should we start digging into Pi v6?
Remember how we talked about the boot process? Well, Pi v6 has its own bootloader, the initial piece of code that sets the stage. It's a combination of assembly and C, and it does the same job as the BIOS bootloader we discussed, just tailored for Pi v6.
Okay, so it's loading Pi v6's kernel into memory, getting it ready to take over. Does this Pi v6 bootloader shed light on any new concepts?
It reinforces the idea that even though the boot process is intricate, it follows a logical flow. The Pi v6 bootloader sets up the CPU, checks for the disk, loads the kernel from disk into memory, and then jumps to the kernel's entry point.
It's like setting up the dominoes in just the right way so they can all fall in sequence.
A great analogy. And speaking of setting things up just right, let's revisit memory management in the context of AppV6. Remember our discussion about protected mode and the global descriptor table? XV6 uses paging to manage memory. which is a more advanced technique.
Paging, that's where the virtual address space is divided into chunks called pages, right?
Exactly. These pages can be mapped to physical memory frames, but here's the cool part. They don't have to be contiguous. The operating system can scatter pages throughout physical memory and keep track of where they are.
So it's like having a giant puzzle, where the pieces can be placed anywhere on the board, as long as you have a guidebook telling you where each piece goes.
Precisely. And this flexibility allows the operating system to manage memory more efficiently. It can swap pages in and out of memory as needed, which is essential for running multiple programs. And even giving the illusion that a program has more memory than physically available, that's virtual memory.
Wow, it's mind-blowing. How much complexity is packed into that seemingly simple act of running a program. And we can actually see how paging is implemented in XV6.
Absolutely. You can dive into the XV6 source code and see how the page table manipulation code works, how page faults are handled, and how the virtual to physical address translation happens.
It's like having X-ray vision into the memory management system.
Now let's shift our focus to another essential component of any operating system, the file system. Think about how you organize files on your computer. You have folders within folders, files of different types. XV6 has a simple file system that, while not as sophisticated as modern file systems, captures the essence of hierarchical file organization.
So it's like a scaled-down version of what I see when I browse my files.
Exactly. XV6 uses the concept of inodes, which you can think of as index cards for files. Each inode stores information about a file, its size, permissions, timestamps, and most importantly, pointers to where the actual data blocks of the file are stored on the disk.
So the inode is like a file's fingerprint, unique and containing vital information.
That's a great way to think about it. And XV6's source code shows how these inodes are managed, how files are allocated and deallocated, and how the entire directory structure is maintained. You can even see the code for common file operations like creating, opening, reading, writing, and deleting files.
It's like having a behind-the-scenes tour of how a file system works from the ground up. And all of this is happening in XV6, our miniature Unix world.
It is. Now remember our discussion about device drivers, acting as translators between the operating system and the hardware. Well, XV6 has drivers for essential devices, like the keyboard, the console, and the IDE disk controller.
So we can see how XV6 interacts with the hardware we use every day. That's exciting.
Absolutely. You can examine the keyboard driver to see how it captures your keystrokes, or you can delve into the IDE driver to see how it reads and writes data to your hard drive.
It's fascinating to see how those abstract concepts we discussed translate into real working code. It's like XV6 is giving us a backstage pass to the digital world.
It is. And while XV6's drivers are simplified, they provide a solid foundation for understanding how device drivers work in more complex operating systems.
This XV6 deep dive is bringing everything together beautifully. We're seeing the theory in action, and it's starting to make a lot of sense. But before we wrap up part 2, there's one more crucial aspect of operating systems we haven't touched on: processes. How does XV6 handle running multiple programs, seemingly at the same time?
You're right. That's an essential piece of the puzzle. XV6's approach to process management is rooted in the design principles of early Unix systems. It uses a straightforward scheduling algorithm, a limited set of system calls, and a clear approach to process creation and termination.
Okay, so XV6 is showing us the fundamentals of process management.
Exactly. You can examine the scheduler code to see how it decides which process gets to run next. Or you can study the system call handling logic to understand how processes interact with the kernel, to request services, like reading from a file or sending data over the network.
It's amazing to think that all of this intricate coordination is happening behind the scenes, constantly and seamlessly, so we can have a smooth computing experience. I'm starting to appreciate just how much work the operating system is doing.
It is a testament to the power of operating systems and the brilliant minds that design them.
XV6 is proving to be an incredible learning tool. It's like having a working model of a computer right in front of us. But I have a feeling there's still more to uncover.
You're right. We've covered a lot of ground, but there are a few more fascinating aspects of operating systems waiting to be explored. We'll delve into those in the final part of our deep dive.
I can't wait. Welcome back to our final act in the world of operating systems. It's like we've been on this backstage tour of a grand theater, seeing all this intricate machinery, all these hidden mechanisms that make the performance possible. From bootloaders to paging, from file systems to device drivers XV6 has shown us how the magic happens.
It's been quite a journey, and we've saved a few more fascinating insights for this final part of our deep dive. These are the concepts that really demonstrate the power and complexity of operating systems, even one as simplified as by V6.
Okay, I'm ready for the grand finale. What other wonders are hidden in the code?
Let's think about how you use your computer. You might have multiple programs running at the same time, a web browser, a music player, a text editor. It seems like they're all running simultaneously, but most CPUs can only execute one instruction at a time.
So how is that possible? How does the operating system create the illusion of multitasking?
It's all about time slicing and context switching. The operating system acts like a master conductor, giving each process a small slice of CPU time before switching to the next one. This switching happens so rapidly that it creates the perception of parallelism.
It's like a digital juggling act, keeping multiple balls in the air at once.
Precisely. And BiV6 implements a simple form of concurrency. If you peek into BiV6's scheduler code, you'll see how it decides which process gets to run next, and the mechanisms for interrupting a running process to switch to a different one.
It's amazing to think that all of this is happening behind the scenes, constantly and seamlessly, so we can have a smooth computing experience. I'm starting to appreciate just how much work the operating system is doing.
Now, when you have multiple processes running concurrently, it creates some interesting challenges, especially when they need to share resources like files or memory. Imagine if two processes tried to modify the same file at the same time. It would be a recipe for disaster.
Like a digital game of tug of war, each process pulling the file in a different direction.
Exactly. To prevent this chaos, operating systems use synchronization mechanisms to ensure orderly access to shared resources. These mechanisms act like traffic lights, controlling the flow of processes to prevent collisions.
So it's all about making sure that only one process can access a critical resource at a time.
You've got it. These mechanisms prevent what are called race conditions, where the outcome depends on the unpredictable timing of multiple processes. And BiV6 uses a simple but effective mechanism called spin locks. For synchronization, a spin lock is like a digital busy sign. If a process wants to access a shared resource, it checks the spin lock. If it's locked, the process has to wait until the lock is released.
So it's like waiting in line at a popular restaurant. You have to wait your turn before you can be seated. Now, we've talked about processes running concurrently and sharing resources. Is there anything else these processes might need to do together?
That's a great question. Sometimes processes need to communicate with each other, and operating systems provide mechanisms for inter-process communication, or IPC. Think about it as a digital postal service, allowing processes to exchange information.
So it's like sending messages back and forth, even though the processes might be running in completely different parts of the system.
Exactly. And BiV6 uses a simple IPC mechanism called pipes. A pipe is a one-way communication channel between two processes. One process writes data into the pipe and the other reads from it.
So it's like a digital game of telephone, passing messages along a chain.
That's a fun way to think about it. And with that, we've come full circle in our exploration of operating system concepts. We started with the moment you press the power button, and now we've seen how the operating system juggles multiple processes, manages their access to shared resources, and even enables them to communicate with each other.
It's been an incredible journey. We've seen how seemingly simple actions like running a program or opening a file involve a symphony of intricate operations happening behind the scenes, all orchestrated by the operating system.
It's a testament to the power of abstraction and the ingenuity of the countless engineers who've contributed to this field. We've only scratched the surface, but I hope this deep dive has given you a deeper appreciation for the hidden world that makes our digital lives possible.
Absolutely. And for our listeners out there, I encourage you to keep that spark of curiosity alive. Take a look at the BiV6 source code yourself. Explore other operating systems, or delve into the vast world of operating system literature. There's always more to learn and discover in this endlessly fascinating field.
Keep exploring and never stop asking questions. That's the heart of true learning.
And on that note, we'll sign off for today. Until next time, keep diving deep.